Oh, now it is exactly, yes. So we resume our seminar, and our speaker is Anar Dosi, Professor Dosi. So I give him the word. So we begin to listen. Anar,
Okay,
please begin.
Yeah,
okay.
let me share my screen first.
Yeah.
Is it all fine?
Yes, I see. Please,
yes. Okay, now it looks better.
Yeah.
Okay. Yeah, okay. Yeah, thanks for the invitation. Sorry, let me up. Yeah, non-commutative complex analytic geometry of a contractive quantum plane.
Yes.
Briefly about some historical moments or introduction. So what is the non-commutative geometry? We know, right? So it's a sort of assignment geometric object to a non-commutative, say, associative algebra of a fixed field. So it's a ringed space. We have in a topological space and structure sheaf. So we used to say, like, if you have an algebra, you can get this geometric object that stands behind of A, and you can restore the algebra itself by means of global sections. That's a main principle of non-commutative geometry. Okay. Well, in algebraic geometry, we know what's happening, right? So anti-equivalence between the categories of commutative rings and defined schemes. In complex analytic geometry, we have an anti-equivalence between the categories of a locally compact topological space and the commutative sister algebras. Well, what does non-commutative geometry mean? So, I mean, complex analytic geometry. Complex analytic geometry deals with the Banach space representations of non-commutative complex algebra. So a geometric space, again, it's a ringed space of a build-up by means of a finitely generated non-commutative complex algebra A. It consists of analytic space and non-commutative Fréchet algebra. Well, it used to be presheaf. It's sometimes can be presheaf or sheaf. So that the, again, global sections represents now the non-commutative algebra of all entire functions in the generators of A. Yeah, that's a main principle of non-commutative complex analytic geometry. So what does mean entire functions? We know. So the abstract characterization of all algebra of, well, let's say non-commutative entire function was proposed by Alexander Yakovlevich and Taylor. It's well known in the literature like Arens-Michael envelope of an algebra. So what is that we know? It's a completion of A with respect to a family of all multiplicative seminorms, of all possible multiplicative seminorms on A. Well, for example, if A is algebra of polynomial functions on a complex affine algebraic variety, then Arens-Michael envelope of A turns out to be the algebra of all holomorphic functions on X. Yeah, that's the result due to Alexei Perkovsky, so to 2008. Well, in particular, if you get this polynomial algebra, we come up with the standard algebra of all entire functions of n variables, x1, xn. Right, that's a routine. So, well, in the case of a non-commutative polynomial algebra, again, Arens-Michael envelope represents the algebra of all entire functions in non-commutative variables generating A. That's sort of treatment like that. For example, if it's a universal enveloping algebra of a finite dimensional nilpotent Lie algebra, then its Arens-Michael envelope is an algebra of all non-commutative entire functions and elements of this nilpotent Lie algebra. For example, you can see my work on absolute basis problem in this algebra, and so on. Well, more detailed and deep analysis of the non-commutative Arens-Michael envelopes done by Alexei Perkovsky in his several big papers within 2006 to 2009. Well, some of them I will mention a bit later, so you will see. So what we're going to do in the present talk. So I wish to explain non-commutative complex analytic geometry of Manin's quantum plane. So what is that? We know what is that, right? It's the quotient of the free algebra in two variables, x and y, modulo this sort of relation, xy equals q minus 1, yx. Q is a complex number apart from 0 and 1. So this is our non-commutative algebra. We wish to understand what kind of geometry behind of this within the non-commutative complex analytic geometry. Yeah, certainly the first target must be its Arens-Michael envelope. So look, that's a notation by Alexei. So AQC2 is the Arens-Michael envelope of this algebra. So if additionally they are invertible, we say that it's all about quantum two-torps. Well, if Q is not 1, we use the terminology contractive quantum plane. Okay, so we wish to understand what's the ringed space behind of this Q plane. What is that? Okay. Yeah, first of all, Arens-Michael envelope. There is a full description, again, due to Alexei Yulich. So it's indeed algebra of entire functions in two variables as a Fréchet space. Look, this is my semi-norms. Is given by like that. If Q less than or equal 1. If Q more than or equal 1, we have a bit modified version. Look, we have Q power minus 1 here. You're adding up. So this is a space of all absolutely convergent power series in two variables, x and y. Well, again, the case of Q more than 1 and Q less than 1, they are very symmetric. I mean, they can be reduced to each other. For example, you can flip the variables x and y if you wish. Anyway, so if Q, we have two main cases. Absolute value Q is 1 or is not 1. Okay, so what we did in the commutative case, let's look at the space of all continuous characters of the Arens-Michael envelope, OQC2. Yeah, well, it should be like sort of our analytic space, right? And we are planning to build up some presheaf of non-commutative fresh algebras extending this algebra. That's our main target. Okay, now let me start some technical part. They're not so hard, a bit elementary. So I have a bit general terminology concerning Q plane. Yeah, by a Q plane, I mean any associative algebra generated by two elements, x and y, with the relation. So by Q algebra, I mean just the quotient of this one, the free stuff. So let me use notations like standard notation I'm going to use throughout all my talk. So Ix, Ixy, Iy. So Ix is a unital, look, that's written here, description, is a unital subalgebra generated by X. Mm-hmm. Plus non-negative integers. So the sort of all polynomials in X. Iy, look, pay attention here, it's N, is a non-unital subalgebra generated by Y. So my unit is here. Ixy is just two-side ideal generated by X times Y. So you can easily see that AQ, every Q plane is just the span of all ordered monomials. Because we can easily flip them. Once you're flipping it, the Q pops up, so no problem. So whatever non-ordered monomials can be written as the ordered one. So for example, Ixy will be this one. Sum of all combinations when Ik at least 1. So overall, my algebra is just sum of these three subalgebras. This one is a two-side ideal. This is a unital subalgebra. This is a non-unital subalgebra. So it's not so hard, right, to see it. Mm-hmm. So what does mean Banach Q plane? By we mean a Banach algebra norm completion of any Q plane. We say that is a Banach Q plane. So just norm completion. Well, at the same time, we can use again the closures of this subalgebra as an ideal. So Ix, if you get this Ix, which will be like this sort of calligraphic Ix, Ixy, Iy, they are closures of the stuff. So Ixy is actually closed two-side ideal. Ix and Iy, they are closed subalgebras. Again, if Q less than 1, we say it's a contractive Banach Q plane. This is our terminology. Okay, look, the first technical lemma is not so hard to prove it. So it tells you the following, like if AQ, a contractive Banach Q plane generated by X and Y, if you take any polynomial from Ixy, then F turns out to be quasi-nilpotent. So all these polynomials from the two-side ideal generated by xy, they are quasi-nilpotents. Well, the reason is not so hard. For example, you can easily prove that xy is quasi-nilpotent because, well, for spectrum, you can flip it. But once you're flipping, Q pops up. But absolute value, I mean, the Q is not 1, so this is squeezing, right? So eventually, sigma xy should be 0. So xy is quasi-nilpotent. But for any polynomial, you need to just take the polynomial. Let me show you again what kind of, look, this sort of polynomial. You need to calculate its powers and prove that it's quasi-nilpotent, spectral resolution is 0. Okay, but there is a problem. Is it true that if you pass to closure, it still is going to be quasi-nilpotent? This one may not be true. So look, the following assertions are equivalent. So AQ, again, contractive Banach Q plane. Then this ideal exactly is inside of the Jacobson radical. Or Jacobson radical consists of all quasi-nilpotents. And Q is commutative modulo Jacobson radical. All these three assertions are equivalent. Look, the third condition is interesting, right? It's important for us, especially if you wish to have a joint spectral theory or sheaf structures. It's better to have this one, this property. Okay, but when that's possible, so to have this sort of property to be a commutative modulo Jacobson radical. Look, for example, in this case, let's look at this operator Q plane. Two bounded linear operators, say T and S, for example. If one of these generates a compact operator, then this property holds. That's true. Again, the reason is simple. If one of them is a compact operator, all ideal of polynomials, they consist of compact operators. If you pass to, but all of them, they are quasi-nilpotent. If you pass to limit, you can use the property of continuity of spectrum over compact operators. As a result, you're getting like the closure is again from the Jacobson radical. Look, this typical example, T and S, shift operator, diagonal operator. These two guys, they're generating the Q plane. Look, this is a famous example of T and S. So if Q is less than 1, the S, look, can you see S is a diagonal operator? So the diagonal tends to 0, so it turns out to be a compact operator. So the associative, closed associative hull of T and S will be commutative modulo Jacobson radical. Look, this is a typical case when this happens.
Yeah.
Okay, now let's look at another type example. Again, this example due to Pekovsky, so what we can do here. Again, we can get Banach Q plane, Q less than or equal to 1, take a number which is dominating norms of X and Y. And look at this correspondence. Look at the absolute correspondence. Suppose it defines a continuous mapping. So continuous mapping means that this one will be a new norm, which is equivalent to original one, right? And certainly if this is a map, this one means my algebra is almost free. So AQ is actually will be free plane, right? Free Q plane. And this one is going to be a norm here, new norm, which is equivalent to original one. So for this algebra, we'll use a notation special, AQ rule. AQ rule. Well, actually, we met this algebra earlier. Look, this again is in the work of Tchaikovsky. So this is a Banach completion of the quantum plane. So that means that actually this norm is multiplicative. If Q more than or equal 1, you can just change it a bit slightly like that. So this analog of holomorphic functions on the closed disk of reducible rule. And our Arens-Michael envelope will be inverse limit. But first, let me say about the same structure of ideals. Again, the same notations, IXY, IX, IY. We used to write IX rho here, adding up a rho. In this case, my algebra is decomposed into topological direct sum of closed subalgebras. So this is a unital subalgebra. This is a non-unital. This, again, two-side ideal. But this ideal is actually intersection of all continuous characters. In our case, the characters of the Banach algebra. So if Q is not 1, again, the middle one is a Jacobson radical. And A rho is a commutative modulus Jacobson radical. But if Q is 1, all quasi-nilpotents will be inside of this ideal. And none of these polynomials or monomials, none of these will be quasi-nilpotent. So the radical is here is really small. I couldn't prove that as a semi-simple algebra, but anyway, something closer to this one. Radical is very tiny, but I can't prove that directly. Why is it semi-simple or not? Anyway, if Q is not 1, we have a nice case. The middle one is a radical. So we have two subalgebras. Algebra's commutative modulus Jacobson radical. So it's all fine, right?
Okay.
So Arens-Michael envelope is the inverse limit of these algebras. I said about it, right? So by passing to inverse limit, you can easily get this decomposition again for Arens-Michael envelope. So this is a subalgebra unital. This is non-unital. This is a two-side ideal. Jacobson radical inside of this ideal, which is intersection of all continuous characters now. So continuous characters, you can kill this ideal, right? If you kill this ideal, you will get something like that, a union of two complex planes. Look, C, 0, 0, C. This comes from the identity, like xy equals q minus 1 yx. So our continuous characters is just union of two complex planes whose intersection is just single 0. Yeah, that's a description of the Arens-Michael envelope. What we got here. Okay, so if Q is not 1, I told you, algebra is nice, commutative modulus Jacobson radical. We have a full description of the radical. It's ideal IXY. But if Q is 1, was a nilpotence inside of this ideal, and none of these monomials, they are quasi-nilpotent. So for this case, Q is not 1, I'm using this sort of notation, AQ CXY. Now CXY because it's a space of all, our spectrum, space of all continuous characters, instead of this one. Okay, now let's switch to elementary stuff. Forget about it, whatever I said so far. Let's look at the complex plane and some exotic topologies that I wish that I need for my statement of the result. So again, fix Q. From now on, Q is less than 1. A subset is called q-spiraling if it contains the origin and it contains this spiraling sequence for every x. So you can imagine, right? So if you take any x, you're rolling, squeezing towards 0. And 0 must be in. Okay, so S q spiraling means actually it's q hull should be inside of S. Well, for example, if you take the small disk centered at A of radius r, if you multiply by qns, you will end up with a sequence of small disks rotating about origin towards 0, right? So that's the meaning of spiraling there. Well, if Q is a real Q-spiraling set means it's just sort of star-shaped set. It's a star-shaped set, like centered at the origin. Well, if you have a single point X, so you know what is that, right? It's a spiraling sequence. Look, Q power n X and 0 as well. So it's a compact set. It's a Q hull of a single point. So just some structure generated by Q number. Well, an open subset is said to be Q open if it's a Q spiraling open set. Open means in the standard topology of C. So it should be open and Q spiraling. So certainly it contains 0 always, origin. For example, all plane is Q open. Empty set is assumed to be Q open. And if you pick them up all Q open sets, it defines a new topology, right? Intersection of Q open is a Q open, whatever union is Q open. So we are getting some topology here, which is weaker than the complex topology, I mean, the standard topology of the complex plane. So that's called Q topology. Well, you can make it a bit weaker. For example, you can just focus on this disks, open disk centers that 0. Again, if you pick them up, it also generates a new topology. So disk topology. This topology is weaker than the Q topology, right? Because every disk centered at 0, it's a Q spiraling set. So we have two topologies, Q and D. Both are weaker than the standard topology, and D is weaker than Q. Well, some exotic stuff, for example, be careful with these topologies, because they are very weak. For example, 0 is a generic point. 0 is dense everywhere, right? Because it contains every open set. So 0 is a generic point in both topologies. For example, you can take any non-zero point and look at the closures. I mean, the closure of single point. Look, if you take the closure of single point with respect to Q, you're getting a sequence which goes to infinity. So it's unbounded stuff. But this is much weaker if you get the D closure, disk closure. You have to sketch the disk of centered at 0, reduce its absolute value x, and look at its complement. So it's massive. The closure of single point is the complement of the open disk. It's a huge closure, I mean. Okay, so the first Q topology is a bit good. It satisfies the axiom T0. As you know, for any 2 points, there is a neighborhood of one of them which doesn't contain the other one. That's T0. So it's a irreducible topological space because every 2 open sets, they have a non-empty intersection. It's not quasi-compact, and it's not Noetherian. And every non-empty open subset, Q connect and Q dense automatically. This is a really weak topology, see here. Okay, what about compact sets here? So if K is a compact set in the standard topology, then it's going to be quasi-compact. You know, it's a quasi-compact subset of CQ. But never expect closedness, right? So we have seen that the closure is so huge, the topology is so weak. So I never expect this property to be closed. But quasi-compact, yes, it is a quasi-compact. For example, if you take all bounded disks centered at the origin, they're all quasi-compact, dense subsets. Okay, some description of these two topologies. For example, disk topology and q-topology, they have the same neighborhood filter base at the origin, right? At the origin, they are the same. I mean, the same filter base. Quasi-compact subset of the disk topology, they're exactly bounded sets. So every bounded is here is quasi-compact, and conversely, every quasi-compact is bounded. But for q-topology, it's quasi-compact if and only if it's quasi-compact is q-hall. Certainly is also bounded automatically. But don't think that every bounded set would be quasi-compact in q-topology. Look, that's example. If you take the unit circle, remove the point 1, this set will be bounded, right? So, but it's not quasi-compact. Anyway, this is something you can sketch it and you can see that it's not a quasi-compact. You can get some infinite covering, which is impossible to get defined covering here. Okay, so that was sort of excursion to general topology. Now let's talk about the sheaves. So again, fix the standard sheaf of stalks of holomorphic functions. And let me draw the sheaf toward my topological space CQ. So formula is called the direct image of the sheaf. So direct image just means you're going to restrict your sheaf to open sets from here. Q spiraling open sets. So we have a notation OQ for the sheaf. Again, it's a fresh algebra sheaf on the topological space. You can use the same semi-norms, but K is going to run throughout all Q compact sets. That will be enough. Just take the Q compact sets. So OQ, O is just OU, is the same, right? Well, we can also introduce OD for disk topology. It's exactly the same. Again, it's exactly the same. So if you take the disk, just the same algebra for holomorphic function on this disk. So they also are commutative fresh algebras, right? So we have two notations, OD, OQ. Yeah, but don't think that they are the same sheaf. No, they are totally different sheaves. Look what's happening here. If you look at the stalks of the sheaves, OQ and OD, both at 0 is the same, right? Because the neighborhood filter base at 0 is the same. So we have the same stalk and the same residue field. But if you look non-zero point, look, for non-zero point, its stalk is just algebra for holomorphic functions on this compact set, algebra for stalks on this compact sets, Q hall of lambda. So it can be decomposed like that. Look, O0 plus all the rest. They are stalks of standard sheaf at single point here, Q and lambda. Well, for D topology, we have this one again, the algebra for all stalks of holomorphic functions on this closed disk of radius lambda centered at 0. Yeah, can you see the algebra is not local anymore? It's something else. Yeah, you can talk about this ideal of those stalks, which is vanishing at this one. Well, you can again talk about residue field, but it's not a field anymore. The residue field looks like that. It's decomposed in the infinite sum, right? Okay, so we got two sheaves as well, so OQ, OD. Okay, now let me introduce. So let's turn back to CXY. Do you remember CXY? That was a space of all characters, continuous characters of the Arens-Michael envelope. It's a union of two copies of the complex plane. So for X, we're gonna equip with the Q topology. For Y, disk topology. Both are embedding here. We're gonna endow with the final topology, right? So that both embeddings are continuous. Yeah, so CXY consists of, look, this is open sets. We say it's a Q open. So this is a, from Q topology, this is a disk just. UY is just disk, right? Radius RY. So CXY is a union of two irreducible components whose intersection is a unique generic point. So the center is dense. We have two lines. I mean, well, one-dimensional complex lines. They have an intersection here and two irreducible components. Okay, on the left, we're going to look at the sheaf OQ on this one. On the right, OD. Well, there is some technical moment. I'm introducing subsheaf whose stalks vanish at the origin. We know every Q open set contains the origin, so I can talk about this subsheaf of stalks would vanish at the origin. So IQ is an ideal whose unitization will be OQ. In the same way, I can introduce ID for the disk topology. So also unitization will be OD. Okay, so I have two ringed space. Look, CX OQ, CY OD. Left one with the OQ, this one with the OD. The two ringed space. Now let's introduce that geometric space that I promised in my introduction. So what is meant contractive quantum plane? So by contractive quantum plane, we mean, again, ringed space, CXY. This is my topological space. This should be our sheaf or presheaf. So formula is a projective tensor product of the left-hand side with Q topology and the right-hand side. So I'm saying unitil projective tensor product of two ringed space. So what is that? Underlying space is the same. We know QD topology, but the presheaf is just projective tensor product. I use the unitization here. Look, OQ to OD. Projective tensor product. So it's a presheaf. Certainly we can talk about the sheaf associated with the presheaf. Yeah, why unitization? So look, if one of these parts, UX or UY, is empty, then I have a C, I'm getting OQ or OD. So this sort of presheaf extending OQ and OD, right? Yeah, this is a structure. So look, this is a contractive quantum plane, what I mean. Yes, so we know how to classify the stalks. So because we know if you restrict to left-hand side, left plane, it will be OQ lambda. We know the description. On the right-hand side, it's different. But at zero, if you look at the stalk at zero, it's going to be inductive limit of the stuff. So it's a limit of this algebra of all holomorphic functions in two variables, so UX, UY. U is running over all QD open sets. Now you will see more detailed description of the stalks at zero, especially what's happening at zero. Okay, so now let's take QD open set. Remember, this side, right-hand side is a ball, I mean the disk, open disk. Then my projective tensor product looks like that. They are like formal power series with coefficients from this algebra of holomorphic functions. Look, I have a family of seminorms, defining family of seminorms, PK rho. So what you're doing here, for this one, I'm taking the standard seminorm, the sup seminorm over a compact set, K. K is a quasi-compact set. Rho is just less than Ry. So I'm taking those power series, or formal power series, which in some sense absolutely converge. Okay, so that's like a Fréchet space. It can be described like that, with a defining family of seminorms. Okay, so my sheaf or presheaf is actually inside or subsheaf of this one, or Q formal power series over Q. Well, we can flip the X and Y. We can flip the topologies. For example, we can equip CX with D topology, CY with the Q topology. This also makes sense. So I'm using this sort of notation, CXY opposite. And in this case, as my structure presheaf, I have to take the formal power series like that, X power n, Fn y. Look, Y is running now over Q open sets. With respect to X, we have a disk behavior. Again, the family of seminorms, they are the same. Look, I'm sorry, yeah, with the same defining family of seminorm. So it makes sense, right? So I can define CX opposite and with the structure presheaf. Okay, now key moment, but where is my multiplication? Look, this is my multiplication, because this should be, we're expecting to have something non-commutative, right? To extend my Arens-Michael envelope or original algebra. Look, if you take the two sections, or say F and G, formal power series, look, we are multiplying them like that. It's again formal power series. The pay attention interior, the brackets, it's a standard commutative multiplication of two holomorphic functions. But q to the I pops up here. Yeah, by the way, q to the ix is from this q hal, right? So q hal is inside of my set by assumption, because ux was q open spiral instead. That's why this must be in. So actually, what I've said so far is they were all about subjected to this multiplication structure, right? Because this is the main moment here. Multiplication looks like that. So this is a standard multiplication. This associative multiplication, you can easily verify the standard multiplication. Yes, so concerning multiplicative seminorms, again, so this is a Fréchet space equipped with the formal Q multiplication. Turns out to be Fréchet, non-commutative Fréchet algebra. Defining family of seminorms, you need just to take as a K Q compact sets. Q compact sets, they are defining the same topology, and rho again the same, less than Ry. So this turns out to be a Fréchet, non-commutative Fréchet algebra, sheaf over on CXY, right? Well, concerning the stalk at 0, so those couples, then for stalks at 0, you can choose two disks, epsilon x, epsilon y. And look at this absolutely convergent stuff. Even this norm can be replaced by this absolute convergent norm. So instead of this, you can write an epsilon x. And probably it's here, let me show you. Anyway, so we know this definition when we had a number here. It's just absolutely convergent series with a certain powers of epsilon x. Yeah, look, this is a sort of, description of the stalk at 0 of the sheaf. What's happening at, it is quite complicated what's happening at 0. Okay. Well, again, if ux is going to be a disk, then I can replace my family of sub norms over K by this one. Then my semi-norm PK rho can be replaced by this one. So as a result, if you take U all quantum plane, you're getting Arens-Michael envelope, or QC2. Yeah, that was algebra introduced by Pekovsky, right? We're getting the same algebra, Arens-Michael envelope. So this is a sort of presheaf extending our Arens-Michael envelope. Yes, we have also, I told you, we have also opposite quantum plane, flipping topologies, X with the D topology, Y with the Q topology. Again, you can take this formal power series and multiply them. Look, the rule is almost more or less the same, right? Just X and Y flipped. But pay attention now, Q power J that pops up here in the first variable. This is in the second one, right? Fi Gj Y. I plus J to Z. Again, this one defines a Fréchet algebra structure. So this is a non-commutative Fréchet algebra presheaf. Well, flipping actually is almost isomorphism, so twisting morphism. You can look at the twisting morphism of two ringed spaces. Look, ZW, you can flip them WZ. And for the sections, you can flip X and Y like that. Yeah, so this is going to be, well, this sort of morphism of the ringed spaces. Yeah, pay attention, this part, this opposite means multiplication is opposite. So we are taking original sheaf and we're going to equip it with the opposite multiplication. So if you do opposite, so you will get isomorphism. So flipping X and flipping the topologies DQ or QD, so they are more or less the same, up to changing multiplication into its opposite. Yeah, again, if Q moles and 1, I told you, we can flip Y and X now. So you will get very similar structure. So that's why, so Q moles and 1, Q less than 1, they're the same. Okay, yeah, let me formulate my first key result. So concerning the description of this sheaf or presheaf, yeah, let's take QD open set. Then my OQU, this is non-commutative algebra, is decomposed like that. So look, this is a unital subalgebra. This is a commutative subalgebra of standard holomorphic functions on the open set UX. UX can be quite a complicated open set, quite a general open set, but this guy is a disk. UY is a disk, and this is ideal of those holomorphic functions vanishing at 0. The middle one is a Jacobson radical. So look, we have a decomposition into a topological direct sum. Again, algebra is commutative, modulo Jacobson radical, and continuous characters, they are reduced to U. U is a union again, UX and UY. Yeah, look, this is the first Q result. Yeah, the proof is not so straightforward. Certainly it's extending the original decomposition for Arens-Michael envelope I told you in the beginning of my tour. But to prove something like that, you have to use sort of holomorphic functional calculus and so on, integral representation. And eventually you can prove something like that. That's good for us to have this sort of description. Okay, look, surprisingly, Stork at 0 is a non-commutative local algebra. It behaves like a sheaf of holomorphic function. It's a local algebra. And we have this sort of decomposition. Look, this is a Stork at 0. This is a Stork of 0, this sheaf, subsheaf, ID. And this I is an inductive limit of this stuff. So look, this is a unique maximal ideal. So this is a local algebra with the unique maximal ideal. Looks like that. Well, now for the sheaf, not presheaf, for the sheaf, you have decomposition like that. So my sheaf actually contains two copies of the holomorphic functions, or stocks of holomorphic functions, OQ and ID. And the middle one is a sheaf. This is a bit complicated stuff. The sheaf associated to the presheaf of Jacobson radical of OQ. Jacobson radical is not a sheaf, so you can look at the sheaf associated to this presheaf. Look, this is a nice description of the sheaf and the stock at 0. But I told you, stock at non-zero points, they're not local. I mean, there's something else. Okay, next key result. What about functional calculus? For example, could we say something like standard functional calculus for two operators, T and S? Yeah, suppose T and S, the elements of a unital Banach algebra. Look, imagine you have two operators. And let's take U to be QD open set. Is it okay? So every couple certainly defines module structure, I mean the representation, like representation of the Q algebra. So this representation extends up to a continuous algebra homomorphism. Look, this is my functional calculus. If and only if spectrum of T lies in UX, spectrum of S lies in UY. Yeah, surprisingly, in this theory, we got so simple solution to this problem without a concept of a joint spectrum. Even for any Banach algebra, look, I'm not forcing some to be operators. It's just Banach algebra representation with this property, and we have this extension property. So we have an extension, continuous extension, if and only if spectrum of T is inside UX, S is inside of UY. Yeah, but where's joint spectrum? Must be somewhere joint spectrum, right? Okay, look at where. Again, suppose B is a unital Banach algebra, which contains Q plane, like that, TS. And suppose my algebra is good. B is commutative modulo is Jacobson radical. I said about this property in the early beginning of my talk. For example, if B is a Q, this is equivalent to this assumption. ITS is inside of the radical. Okay, let's use this property, B to be commutative modulo Jacobson radical. In this case, the open group of invertible elements is a regularity. So look, this is a definition of regularity. AB is invertible if and only if A and B invertible. Well, if algebra is commutative modulo Jacobson radical, the regularity defines subspectrum. Well, there is a general definition of joint subspectrum. I skipped all this stuff, so more or less, for example, Harte spectrum. Harte spectrum of joint spectrum of the family. Yeah, all the stuff you can see in my work, my older work that I've forgotten completely. So I published this sort of paper 2008. So you can see there, like if B is algebra commutative modulo is Jacobson radical, then you can construct the subspectrum. They're in one correspondence with the regularities. Okay, look. Now let's take Harte spectrum. So what has been Harte spectrum? Maybe you know. So it's all about left invertibility. There's left Harte spectrum, right Harte spectrum. So you should subtract T minus lambda S minus mu and generate an ideal, left ideal. If it's proper, we are saying lambda mu from the joint spectrum, left. In this case, left and right, they coincide, they're the same. This is a Harte spectrum. Again, Harte spectrum strongly depends on the algebra B. It's constructed with respect to algebra B, which is commutative modulo Jacobson radical. Again, in that paper, you can prove that Harte spectrum turns out to be invariant if you pass to quotient with respect to radical. But on the quotient, we have this property, T times S is 0. So you can calculate Harte spectrum on of the quotient. There are lambda 0, 0, mu, lambda from spectrum, mu from spectrum. Well, you can drop these classes because I told the spectrum lives invariant whenever you're passing to radical, a quotient, modulo radical. So you have a spectrum, and eventually you're getting the union of two spectra of T and S. So my spectrum, actually this union, it turns out to be joint spectrum, Harte spectrum. And that union is inside of my quantum plane, CXY. So let me formulate again what I've said on functional calculus. So U, QD open set, we have a representation. Representation extends up to a continuous algebra homomorphism. If and only if joint Harte spectrum inside of B belongs to U. Again, that's a case when B is a commutative modulo Jacobson radical. And in this case, we can also prove spectral mapping theorem for any tuple of holomorphic functions from my presheaf. This nice formula holds again for any function f or analytic function f. Well, example where you can apply it, for example, let's turn back to the same shift operator and the diagonal operator. So let's take operator Q plane, AQ. I told you it's a commutative modulo Jacobson radical. So let's calculate all spectra inside of this algebra. Well, spectrum of T, it's a shift operator, is a unit disk. Certainly, if you look at the spectrum, Harte spectrum, I mean, spectrum inside of this algebra, it can be larger, right? It used to happen like that. It should be larger. But for T is the same. But for S, it can be strictly larger. But anyway, for S, it's also inside of the unit disk. Yeah, let's summarize. So Harte joint spectrum, TS, is a union of the unit closed disk and some set, which is inside of the unit disk. So this is my quasi-compact set. Certainly it's a quasi-compact set. So look at this example. Let's take open set as a union of two disks. And let's take this function like ln 3/2 plus xy. Yeah, again, you should expand it into Taylor series, use the elementary properties, elementary algebra, quantum plane. You will see that this is from this direct sum, OQ and radical. Look, we have plenty of stuff from the radical here. And apply to operators T and S. So again, for T and S looks like that. It makes sense. So you can calculate its spectrum. Look, spectrum mapping theorem works here. Yeah, again, another example, more complicated example. You can generate more examples, exotic examples. Look, ln 3/2 plus x, some terrible stuff here, radical, and some holomorphic function, which is vanishing at 0. Yeah, again, some boring stuff. You can calculate, estimate the norms, right? So yeah, let me show you the result. Anyway, some estimations. So look, you can prove that this sum exactly belongs to this direct sum, as I told you about decomposition. OUX, Jacobson radical, and the other one. So you can calculate its spectrum. Makes sense. You can apply the functional calculus. Spectrum looks like that. Look, this part from the left-hand side, because the middle part falling apart, so this one disappeared. You have left-hand side and right-hand side. So this is a full spectrum of this operator FTS. Okay. Yeah, finally, a few slides. What tells us topological homology in this direction? Or what tells us Alexander Yakovlevich here? So in this case, we have a nice bimodal resolution free for this quantum plane.
Yeah.
Look, this resolution, this result, a nice result due to Tartajan, 1989. Look, you can see the differentials from the left-hand side. It's a nice resolution for, and pi is a standard map, multiplication map, AB, AB. Okay. Well, one of the key results of Pekovsky, about 2008, states that this embedding into Arens-Michael envelope is a localization in the sense of Taylor. Or sometimes Alexei introduced another terminology like homological epimorphism. So that means the homology theory over this one, I mean, topological homology, and over this one, they're the same. So that means if you're tensoring left-right using Tartajan resolution, you can get very similar resolution. This complex is admissible and provides all QCXY free bimodal resolution for our algebra, Arens-Michael envelope. Look, differential almost the same. They're the same, just tensoring left and right. I mean, module tensoring. You're getting this one. Yeah, this is a key result due to Alexei. So we have a free bimodal resolution. So from now we can perform our homological calculations here. Look how. Now let's take left Fréchet module over Arens-Michael envelope. Yes, I can tensoring from the left to my resolution. Look, I am getting another resolution, so it's admissible. This one provides left free or Q module resolution of my module X. This is okay. Again, I'm skipping all this part. You know more what's happening here. The left-hand side, you're going to have module multiplication from the right. Oh, I'm sorry, from the left. From the right, X multiplication. From the left, algebra multiplication. Okay, now let's turn back to Banach module. Suppose X is a Banach module over Arens-Michael envelope. That means we have a couple of operators with this relation, bundling operators. So we define resolvent set of those continuous characters, so that the trivial module is in the transversality relation with respect to left module X. So that means all these homology groups, including zero, they're all vanishing, torsion groups. This is a trivial module versus X. Yeah, so, and its complement, let's introduce sort of spectrum. You know, this idea first implemented by Taylor, and you can see in the book of Hilamsky and the Putinar's work. So Harte introduced the spectrum from this point of view. Look, we're getting some set, interesting set. Well, you can calculate now homology groups using our resolution, right? So if you apply this functor, we'll end up with interesting complex. Look, it's a Banach space complex, parameterized, with the differentials. Look, gamma application to y is a scalar, gamma to x, and the same is here. Is in the matrix shape. This is an embedding here, and this is a mapping into x from sum. So again, spectrum means set of those gammas, which so that the complex is not exact. It's a sort of Taylor spectrum, right? So look at here, gamma of y, gamma of x. One of them should vanish because we have on the left-hand side and right-hand side. So actually we have two spectrum, left spectrum, right spectrum. You can write down sigma x, sigma y. Yeah, but we have a full of surprise. Spectrum is not so good. For example, the projection property failing here. Yeah, look what's happening. Again, let's take our standard example. Shift operator and diagonal compact operator. We know they are spectra. Spectrum of T is disk, closed disk. This is our Q hole. Look, if you restrict the spectrum to the left, Cx, our expectation, this spectrum would be inside of the disk, right? That's the meaning of projection property. But look what's happening. It belongs to dq minus 1. It's getting out. But even more, so it contains the whole annulus out of the unit disk. So it totally gets out and even contains quite a big slice of this disk, dq minus 1. And more, the worst scenario, so it doesn't contain 0. Right? So because our expectation 0 must be here, but actually not. So this spectrum is quite mysterious, are quite different stuff. Well, if Q absolute value is 1, spectrum can be empty. But if Q is not 1, it's not empty. It's a non-empty compact set. This can be proven, it's done. Well, so this spectrum demands something else. It demands quite a different theory. Well, maybe later, not now. Okay, yeah, let me stop here. So finally, what I want to say, everything new is, well, forgetting old.
Yeah. Thank you very, very much for a very interesting talk.
Yeah,
so what are questions?
Yes, please.
What about? Usually Anar has questions, but now
I have no question.
He asked himself. So who else? Who else? Alyosha?
Well, no? Maybe this is not exactly a question, but rather some thoughts about the Taylor spectrum. When you consider your structure space for the algebra, you always take the set of all characters.
Yeah, that's right.
So what if we enlarge the space and consider all irreducible representations? In this case, the Taylor spectral will be a subset of a bigger set, and maybe its behavior will be more will be better than in this case. So maybe projection.
Yeah, you're right. Yes.
And some
yeah,
other
you're right. But if Q is less, if Q is not 1, so we have no other option. So I told you it's a commutative modulo Jacobson radical. So all actually reducible represent they are reduced to characters. If Q is not 1, but if Q is 1, you're right. But if Q is 1, certainly we have to look at all reducible representation. But even this sort of spectrum can be empty.
Yeah.
So this should be quite a different theory. So we should separate here. I don't know. So strange behavior. So, well, at least if Q is not 1, this is a right way. The problem is that we need to change the structure sheaf. It should be something else. It's not like that. And well, I have some work, but still I've been doing it. So I haven't ended yet. So yeah, you're right. Certainly we have to choose the residual representations. But if Q is not 1, so no other choice. That's the case. So
I see.
That's what we have.
Okay.
Thank you.
Okay, other questions or comments or counterexamples? Yes.
Yes.
Okay. In this case, let us again to thank our speaker for a very good and competent talk. And so the next one will be, and the last one in this season will be Denis Fufaev. Yes, and I hope to meet everybody and hear him. And now we depart and let us meet again the next week. So thanks again very much. Bye. Bye.
Thanks. Bye.
Спасибо большое.
Thank
Очень
you
смешно.
very much.
Спасибо.
Спасибо.
You see, people
До
are
свидания.
quite satisfied
Спасибо.
by your talk.
Okay, yes.
Yes. Bye,
Thanks.
bye,
Bye.
bye.
До свидания.
До
До
свидания.
свидания. You see?